Hey, welcome to the podcast.
Thanks for having me.
So, Anya, I've been trying to wrap my head around this whole deep learning thing, and I feel like I'm missing something basic here.
Oh man, I get that all the time. It's one of those things where everyone talks about it, but what actually is it, you know?
Exactly. I know it's AI, but then there's machine learning and then deep learning. It's like Russian dolls or something.
Yeah, that's actually a pretty good way to think about it. So AI is the big umbrella, like all the logic stuff, search algorithms, probability, but machine learning is the part that actually learns from data instead of us having to program every rule.
Okay.
And deep learning is just a way to do machine learning with these really deep neural networks. Like, instead of having one or two layers, you stack up tons of them.
Wait, what makes them deep, though? How deep are we talking?
Dude, sometimes hundreds of layers. Each one is imagine you're looking at a photo, right? The first layer might just see edges, then the next one sees shapes, then objects, then full scenes.
No, what? Really?
Yeah, it's wild. Each layer is basically learning a different representation of the same data. And the crazy part is, these things can handle anything. Text, images, audio, even molecules.
Molecules? What the hell?
I know, you can predict both the melting point and boiling point of some chemical compound at the same time. It's called multivariate regression or whatever.
So it's not just like cat or dog, it can predict multiple things?
Exactly. But here's the thing that really gets me. These networks are finding the best function to fit the data, right? Imagine you're trying to predict a kid's height from their age.
Mm-hmm.
The network is basically searching through this huge family of possible functions to find the one that fits best. But get this. The book I was reading said these functions can be so complex, they have more regions than there are atoms in the universe.
What? That's insane. How does that even work?
That's the thing, nobody really knows. Even the experts are we don't fully understand why these things work so well.
That's kind of terrifying, actually.
Right? But here's what's cool. Some data has structure, some doesn't. If you have a spreadsheet of numbers, the order doesn't really matter. But with images, the pixels next to each other are related.
Oh, like how words in a sentence matter for order.
Yes, perfect example. My wife ate the chicken versus the chicken ate my wife. Totally different meanings because of word order.
Yeah, that would be a very different dinner conversation.
Exactly. So the network has to process sequences differently, but what really blows my mind is structured outputs.
What do you mean?
Instead of just saying, this is a cat, imagine labeling every single pixel in an image or generating a whole image from just a caption.
Wait, so it's not just recognizing stuff, it's creating stuff.
Yes, and it has to learn the rules of what makes a valid output. Not just every random collection of pixels makes a real-looking image, you know?
That's like it's learning a language and then speaking it fluently.
Dude, that's exactly it. That's where generative models come in. They learn the structure of data without even needing labeled examples.
How does that work?
So they use these things called latent variables. They compress the data down to just a few key numbers, and then they can reconstruct from that. I saw this demo where they took two images and morphed between them smoothly.
No way.
Yeah, it's the model learned a map of the data and you can navigate between any 2 points and get something that makes sense in between.
That's how you get those crazy style transfer things, right? Like turning a photo into a Van Gogh painting.
Exactly. The model moves through this latent space to create new stuff. And get this, you can even teach it to translate between different types of data, like turning text into images.
So it learns the language of both text and images?
Yes, and then there's reinforcement learning too, which is instead of just mapping inputs to outputs, you have an agent making decisions in an environment to maximize rewards.
Like a video game AI.
Exactly. Deep networks handle the complex inputs like what the agent sees and decide what actions to take.
This is incredible, but also kind of scary.
Yeah, that's the thing. All this power comes with real risks. Bias, fairness issues, explainability problems. If we don't even fully understand how these things work.
Right, and who controls this technology? What if it gets weaponized?
Those are the big questions we need to be thinking about as this stuff gets more powerful. It's not just about the cool tech anymore.
Okay, Anya, I was reading about supervised learning, and the way it's framed is this mapping from inputs to outputs. Predicting the price of a used Prius based on age and mileage. That basic idea just clicks for me, but the math around parameters and loss functions, I want to make sure I really get that. Can we unpack that a bit?
Totally, Marcus. So think of the model as a family of equations. Each one's defined by these things called parameters that map inputs to outputs. The parameters are basically like knobs you turn to fit the model to whatever data you have.
Wait, so when you say parameters, you mean like the slope and intercept in a line? Because that's what I think of first with.
Exactly. That's the perfect example. Like in basic linear regression, the parameters are just the intercept and the slope. Different values of these make different lines, which are basically different possible models.
Okay, so then the training part is about finding the right slope and intercept that make the line fit the training data best, right? But how do we even know which line is best?
That's where the loss function comes in. It's basically a way to measure how wrong your model's predictions are compared to the actual answers. In the linear regression example, they use something called sum of squared errors. You square the difference between what you predicted and what actually happened, then add them all up.
Oh, so squaring makes sure all errors are positive and like penalizes bigger is more, right?
Exactly, and it also means the direction of the error doesn't matter. Whether your prediction is too high or too low, it counts the same. The model's whole goal is to find parameters that make this loss as small as possible.
So how do they actually find those parameters? Do they just try every possible line until the loss is lowest, or is there like a smarter way?
Trying every possible line would take forever. Instead, they use these algorithms like gradient descent. You start with random parameters, then you keep tweaking them to go downhill on this loss surface until you hit the bottom.
Wait, downhill on a loss surface. So the loss is like a landscape and you're trying to find the lowest valley? That's actually pretty cool to picture.
Yes, the author even shows it as this surface where each point is a pair of parameters and the height is how bad the loss is. Gradient descent basically walks downhill until it can't go any lower.
But what if the loss surface has like multiple valleys? Could gradient descent get stuck somewhere that's not actually the best valley?
That's a classic problem in more complex models. But for simple linear regression, the loss surface is what we call convex, meaning there's just one global minimum, so gradient descent will find it no matter what.
Oh, wow, that's actually reassuring. So once we find the best parameters on the training set, how do we know if the model will do well on new data it hasn't seen?
Good question. That's why we test it. We try the model on a completely separate set of data that it's never trained on. If it does well there, it generalizes well. If not, it might be overfitting or underfitting.
Overfitting and underfitting, I always mix those up. Can you remind me what's what?
Sure. So underfitting means your model is too simple, like trying to fit a straight line to data that's clearly curved, so it misses important patterns. Overfitting means your model is too complex, and it learns weird quirks in the training data that don't actually matter.
Wow, so it's like a balancing act. I guess that's why simple linear regression is pretty limited, huh? It literally can't do anything more than a straight line.
Exactly. And that's where neural networks come in, like the shallow ones we'll talk about next. They break the input space into these piecewise linear regions, which can handle way more complicated relationships.
Wait, piecewise linear? Like many little straight lines connected together? That sounds way more flexible.
Yes, exactly. So like a shallow neural network with ReLU activations can create these joints or breakpoints where the slope changes. So it can fit curves by basically stitching together linear pieces.
Oh man, that reminds me of when I tried to fit a curve using linear splines in stats class. It's like the neural network does that automatically, but with learned parameters.
Exactly. And the way the hidden units turn on or off, they call it active or inactive, depending on what you feed them, determines where those joints are. The network adjusts these during training to best fit the data.
So with more hidden units, you get more joints and more complex functions. Is there like a limit to how complex it can get?
Actually, with enough hidden units, shallow networks can approximate any continuous function as closely as you want. That's this thing called the universal approximation theorem. It's pretty wild.
No way. So basically adding more neurons lets the network get as close as you want to any function, at least in theory.
Exactly. Though in practice, you're balancing how complex your model is, how much training data you have, and computational resources. Also, deep networks with multiple layers can approximate complex functions more efficiently, but that's for next time.
I love how this builds up from simple lines to these piecewise linear functions with hidden units acting like function breakpoints. It's like watching the model learn to bend and flex the input space.
Yeah, and the input space gets chopped up into these, what do they call them? Convex polytopes in higher dimensions. Visualizing that is pretty tricky. But the idea is the network carves the input space into simpler parts it can handle linearly.
Okay, so we just wrapped up on shallow neural networks, right? And how they're like these piecewise linear functions, super powerful for a lot of things. But then you start thinking about really complex problems.
Exactly. And that's where the idea of going deeper, like truly deep with networks comes in. But it's not as simple as just stacking more layers, right?
Right, because you hit that wall, like the vanishing gradient problem or exploding gradients. Suddenly, training a 50-layer network just becomes impossible.
Totally. You're trying to walk downhill on that loss function like we talked about, but the path just disappears or becomes too steep to navigate effectively.
So how did we even get past that? Like, what was the first big breakthrough that allowed us to actually build these truly deep architectures?
Well, one of the most elegant solutions, in my opinion, came with ResNets, residual networks.
Oh, the skip connections, where you're essentially allowing the input to bypass a few layers and add directly to the output of a later layer, right?
Precisely. It's like giving the network an identity shortcut. Instead of learning the entire transformation, a layer just needs to learn the residual difference from the input. It makes training so much easier for really deep models.
That's wild. It's such a simple idea, but it totally unlocked the ability to go from like 20 layers to hundreds, even thousands, and actually get them to train effectively.
Totally. It was a game changer for image recognition especially. Suddenly, we had these incredibly powerful vision models.
And then, not too long after that, we saw the rise of transformers, which honestly, when I first heard about them, I was like, wait, what? No more recurrent networks.
I know, right? It felt revolutionary. The whole attention is all you need paper, it just flipped the script on sequence modeling.
Yeah, because before, with RNNs or LSTMs, you had to process things sequentially, word by word, which was slow and had long-range dependency issues.
Exactly. Transformers, by using self-attention, can weigh the importance of all other words in a sentence simultaneously. It's like looking at the whole picture at once, rather than one piece at a time.
So it's not just faster, but it also captures context way better, which is why it's been so huge for things like natural language processing, right?
Absolutely. Think about machine translation, text summarization, even large language models like GPT. They're all built on the transformer architecture.
And it even jumped into computer vision, didn't it? Like vision transformers, which I still find kind of mind-bending.
It did. It treats image patches like words in a sentence. It's just another testament to how incredibly versatile the attention mechanism is.
That's insane. So we've got ResNets for deeper, more robust networks, transformers for handling sequences and context. What about data that isn't really a grid or a sequence?
You're talking about graph neural networks, or GNNs. This is where things get really interesting for non-Euclidean data.
Like social networks, molecular structures, recommendation systems, where the relationships between data points are as important as the data points themselves?
Precisely. GNNs are designed to operate directly on graph-structured data. They learn representations of nodes and edges by aggregating information from their neighbors.
So it's kind of like message passing, where each node is collecting information from its immediate connections, processing it, and then passing its updated information along.
That's a fantastic way to put it. That message passing thing is at the heart of how GNNs work. Each node effectively builds a representation of its local neighborhood.
That's so powerful. Imagine trying to do that with a traditional convolutional network or even a transformer. You'd have to flatten everything, lose all that relational data.
Exactly. GNNs preserve that topological information, which is crucial for many real-world problems. Drug discovery, fraud detection, even traffic prediction.
So from just stacking layers and realizing the problems to ResNet solving depth, transformers revolutionizing sequences, and GNNs tackling graphs, it's been an incredible journey for architectures.
It really has. Each of these breakthroughs built on the last, pushing the boundaries of what deep learning can achieve.
It's like we're constantly finding new ways to make these models understand the underlying structure of data, no matter how complex.
And the cool thing is, they're still evolving. It's a very exciting time to be in this field. Well, I think that covers the architecture evolution pretty well.
Yeah, this was awesome. Thanks for breaking all that down.
Absolutely. Always fun talking about this stuff.
All right, catch you later.